everyone. Welcome to our 7th lesson of the semester. So last time we finished up learning about trig sub, and we saw how using an algebra technique called completing the square enable us to apply trig sub to more integrals. Now today we're actually going to kind of have that same theme. What we're going to be doing is we're going to be reviewing some stuff from algebra and actually probably learning for the first time for many of you something from algebra that's also going to help us complete integrals. And the technique we're going to learn about is called partial fractions. That's the name of today's lesson. Partial fractions, and this will also be 2 parts. Okay, so one type of function that shows up pretty often in many applications and in mathematics itself are called rational functions. So I'm sure many of you have heard this name before. Does anyone know what a rational function is? What's the definition of that? 1 over x. 1 over x is an example of one. It has ratio in it, so it has something to do with fractions. What's a rational function?
Can be expressed as a ratio of 2, like you can make it into a fraction. Any function that you can make into a fraction.
It's not quite any function. It's usually a polynomial divided by a polynomial. So like p of x over q of x. So this is what we're going to call a rational function. But yeah, that's kind of the right spirit though. We have one polynomial and it's going to be divided by another. Yeah, and we have to say q is not 0. Can't divide by 0. Okay, so these show up pretty often, and we just saw an example of one 1 over x. 1 over x squared plus 1. This is another one. We could have maybe x cubed minus 17x plus 5 over x to the 4th minus 3 halves. All of these are going to be rational functions. And rational functions are pretty common, so we should probably know how to integrate them. The problem is, so we already saw how to integrate some rational functions. Like for example, does anyone know how we would do this one? How would we integrate this rational function?
U sub.
Yeah. Oh, actually, yeah. So we have multiple correct answers. Yeah. So we could use u sub or we could use trig sub to do this. That's right. So we have several. Now we start to have several methods of doing integrals. So this one we could already do. We don't need any new information for that. Let's see here. But on the other hand, let's say we have x squared minus 1 over x squared minus x minus 6. So maybe we could do some stuff with completing the square, but completing the square down here will make this look kind of incongruent to this right here. So maybe there's a way we can do trig sub. It would be terrible though. So I'm just going to go ahead and say that we don't have the technology to do this one yet. So how are we supposed to integrate rational functions? The answer is we just write them differently using an algebra technique called partial fractions. Now before we do that, we actually need to review something else. So how many of you guys remember polynomial long division? Yeah, that's so the audience says, yeah, they remember it, but not how to do it. Yeah, that's a very common reaction. That's how I was when I took calc 2. I hadn't done polynomial long division in forever. So yeah, so the first thing we're going to do is we're just going to review how to do this because we do need to do this for a lot of these integrals. So for example 1, this is a review. Okay, so use long division. And I really want you guys to practice long division. So synthetic division, that's also something you may have heard of. That's nice, but a lot of times we're going to be dividing by things like quadratics. And you can't really use synthetic division to do that. So I would get used to using just regular old long division. So for this example, we're going to use long division to divide, let's see, x squared minus 1 by x squared minus x minus 6. And that's exactly what we have in this integral right here. So in order to use partial fractions, we need the degree of the numerator to be less than the degree of the denominator. But we can't use this new technique on this one because they have the same degree here. So what we're going to do is we're going to rewrite it using long division. All right, so x squared minus x minus 6 is going to be the thing that's dividing x squared plus 0x minus 1. And I like to put like a 0 for missing powers of x, kind of just keep things organized. Now remember, the way we do this is we look at the highest power that we have over here, right? And we think about, okay, what do I need to multiply this by to get the first term right here? And what do I need to multiply this by to get this? 1, that's right. So since 1's a constant, I put it in the constants column. I multiply the whole thing by 1, and then I'm going to subtract it. All right, and if we did this correctly, we should get 0 always for the first subtraction. So x squared minus x squared will be 0. Now we have no x's minus a negative x. That will give us positive x. And then we have -1 minus -6. That's going to be 5 right here. Now, when the degree of this is less than the degree of that, that means we're done. And whatever we have left over here, does anyone remember the name of what this is called, the leftovers? The remainder, that's right. Just like from regular long division. All right, so what does all this mean? What does this 1 mean, this remainder? Where does all this stuff go? So if I want to do x squared minus 1 over x squared minus x minus 6, that's the same thing as whatever we have up here on its own, and then our remainder divided by the original divisor here. So this is another way of saying this function right here. And this way is going to be the way that we prefer because, well, we know how to integrate 1. That's not going to be too hard. And then this has a lower degree than the bottom. And that will always be the case for these remainders. So then we can use partial fractions, which I'll explain in a little bit. All right, so that's kind of a brief review of polynomial long division. So I want you guys to review it too, since we're going to be using it. So our first practice problem is use long division to divide, let's see, what do I have here? X squared plus 5x plus 6. We're going to divide that by x squared minus 3x minus 4. All right, so I'll give you guys a few minutes to flex your long division muscles here. That 1 over 8x plus 10, all that stuff. That seems pretty good. All right, let's see how we would get this done here. So let's use long division to divide this by this right here. All right, x squared plus 5x plus 6. All right, so this example is actually very similar to the previous example in that what do I need to multiply this by to get this? It's going to be 1. Now, it won't always be 1 for long division. Like maybe if this were x cubed, I would multiply this by x to get there, so I'd put an x up here instead. But in this case, it is 1 again. I do 1 times this, and I have x squared minus 3x minus 4. And then remember, I'm subtracting all this. It's really easy to get a sign error right here. So I have x squared minus x squared. Those should cancel out if you did things right. I have 5x minus negative 3x, meaning I'm going to have 8x. And then I have 6 minus negative 4 is going to be 10. And since this degree is lower than the degree of my divisor right here, that means that we're done. So this is my remainder, RE for remainder. So this means that I can express this as 1 plus 8x plus 10 over x squared minus 3x minus 4. And if you're ever unsure of your work, you're like, oh, I'm not entirely sure if I did this. Remember, you can go back the other way by multiplying the top and bottom of this 1 by x squared minus 3x minus 4, and then combining it back. And you should end up back where you started. So you could always kind of check your work that way if you want to. All right, so there we go. So that's our little long division review. So now what we're going to do is we're going to learn something new. And this is actually another algebra trick. This is not specific to calculus. This is just a general algebra trick, but it happens to be useful in calculus. And that's going to be partial fractions. All right, so now that we know long division here, now we're going to apply it to partial fractions. And there are going to be 4 cases of partial fractions. Okay, so before I go anywhere, I want to kind of explain the intuition behind this. So let's say we have this thing that we got earlier, right? Let's say we want to do the integral of 1 plus x plus 5 over x squared minus x minus 6, right? So the first part of that's really easy. The integral of 1 is x, but we still have this part to contend with. Okay. I don't need parentheses. I don't know why I did that. Okay, now we can factor the bottom of this, right? What is the bottom or the denominator here going to factor into? Yeah, something with 3 and 2. Probably x minus 3 and then x plus 2, like that. Okay. Now, the whole idea, this is the main theme. This is the whole idea of partial fractions. What we're going to do is we're going to attempt to split this up, and we're going to have one x minus 3 piece and one x plus 2 piece. So we're going to have something over x minus 3, and then we're going to have something maybe different than that over x plus 2. Okay, and then why would we do that? Well, the integral of 1 over x plus or minus a number is simply natural log of absolute value of whatever that is. So if we can get to this form right here, where we have a number over this and then a number over that, then we're good to go. But from here, it doesn't really look like we could do that. Like you can't split up multiplication on the bottom and turn it into addition, right? Like that's not how fractions work. So how are we supposed to get from here to here? And that's what partial fractions is. Partial fractions is the process of figuring out what these coefficients are so you could split up your rational functions. So now there are going to be 4 separate cases of this. We're going to do 2 of them today, and we're going to do 2 of them on Monday. All right, so let's look at the first case here. Case 1. Case 1 is where the denominator factors into distinct linear factors, i.e. it factors like this. So it factors into x plus or minus something times x plus or minus something else, and then maybe there could be a third one, x plus or minus something else. There won't be anything like x minus 1 quantity squared, and there also won't be anything irreducible like x squared plus 1. It's essentially just going to look like this right here. So that's going to be our first case. And this is probably the easiest case to deal with right here. So I'm actually going to continue to do this example. So this is example 2. And that's something that I already started right here. Okay, so what I need to do now, so if I can get from here to here, then I'm essentially done because these integrals are not hard to do. So essentially all I need to do is get from here to here. Meaning I need to solve for what A and B are. Now, we're actually going to learn several different ways of doing this. And for some problems, one way is going to be easier. For some problems, the other way is going to be easier. For distinct linear factors, the way I'm about to teach you is like always going to be the easiest way. And that's called the cover-up method. Okay, so let's say, for example, we want to figure out what A is, right? So what we do is we first see what's going to make the denominator of A's fraction going to be 0. And that pretty obviously is going to be 3. Then what I do is I come over here, right? And I cover up the term that it shares with A. So it shares the x minus 3, so I cover that up. And I plug 3 into the remainder here. So my A is going to be 3 plus 5 over 3 plus 2. That means A is going to be 8/5. And that's it. That's all you have to do to figure out what these are when we have linear terms like this. All right, so why don't you guys help me with B? So first of all, what x is going to make this bottom here going to be 0? -2, right? Okay. So now we come over here, we cover up the term that it shares with that B term, and then what are we going to get if we plug in -2? Yeah, it's going to be -3/5. That's right. So B is going to be -2 plus 5, and then we have -2 minus 3. Absolutely right. There we go. And then now we have our coefficients. We have 8/5 and then we have -3/5. So now what we could do is we could take our integral, x plus 5 over x minus 3, x plus 2, and we could say that this is the same thing as the integral of 8/5 over x minus 3, and then minus 3/5 over x plus 2 right here. All right. Now, whenever we have an integral that is a constant over x plus or minus another constant, this is always going to be that constant times natural log of absolute value of whatever is on the bottom. But only in this case. I'm going to talk about that a little bit more later, but I probably shouldn't use C. Let me use A. Yeah, so whenever we get to this situation, kind of like we have here, then we could just do the integral. But we're going to be careful about this, and I'll explain why a little later. So when I do this integral, we have 8/5 natural log of absolute value of x minus 3. And then we subtract 3/5 times natural log of absolute value of x plus 2. And then we're finished with the integral. So we have plus c. And there we go. So that's how we use partial fractions, which is an algebra technique, not a calculus technique. It's an algebra technique that we can use to integrate rational functions that we couldn't do before. And the reason why I say this is an algebra technique, take a look at what I'm doing here. So this is the partial fractions method. Notice that there's not a single integral sign in there at all. We could use partial fractions anytime we have something like this. And there's actually going to be another occasion way later on in the course when we're going to be using partial fractions that has nothing to do with integrals. So remember that this is more general than just for integrating. Okay, so now I want you guys to try this. And conveniently, you're actually going to use the practice that you did earlier. So for this, I want you guys to try this integral, x squared plus 5x plus 6 divided by x squared minus 3x minus 4. And this might seem familiar because this is literally the long division that you did earlier here. So you literally did this long division. How did I get this? This is just a general formula. This is how we do integrals like that. And how do I get the x's? They're always whatever makes the bottom of these guys be 0. All right, so we already know, I guess I'll just spoil this with what we had earlier. So we already know that we could write this as the integral of 1 plus 8x plus 10 over x squared minus 3x minus 4, because of the long division. And again, I'll say this, you need to do long division if the degree of your top is not smaller than the degree of the bottom. And since they are the same, we needed to do long division here. So you always need to check that first. If you don't do that and you try to do partial fractions anyways, it won't work. That's right. Yeah, we want the power on the bottom to be bigger.
Can we always do long division?
Yes.
Okay. So I just.
Yeah, in fact, I would recommend not doing synthetic division because I'll see a lot of the times we're dividing by something higher than a first power. So I would avoid synthetic division. Are we allowed to simplify? I don't really see how we can simplify this one. Oh, you could factor out a 2 from the top. Yeah, there's no problem with that. Yeah, so you can pull out a 2 from the top, do your partial fractions, and then just put the 2 back in when you're done. Yeah, that's totally fine. What would be inside the long division root? It's whatever it's whatever the thing you're dividing by is. Or no, sorry, it's the thing being divided. So this x squared plus 5x plus 6 would go in there. Yeah, this is literally the problem that we did earlier. We actually already did this long division. I set that up on purpose. So you see the top part goes under the root here, and then the bottom part goes on the outside. I'll give you guys a few minutes to work on this.
Is it a coincidence that the denominator of our a and b are the same?
To be honest, I don't remember what they are. So I don't know if I don't know.
For the first case that you gave us, we got like 8 over 5 and negative 3 over 5. Like the denominators for those are the same, and even with this problem, it's
Oh yeah, it might be over 5. I mean, that's a pretty common denominator. Yeah, that's entirely possible.
Is there a reason for that, or is that just like a coincidence?
It's really a coincidence.
Okay.
All right, give you guys another minute or so to work on this. That's good. Yeah, that's partially what the practice problems are there for. It's increasing your confidence. It's also why I recommend that you practice so much, because if you practice it, you start getting them right, then you become less afraid of it and you want to practice more. It's a nice feedback loop. All right, let's go ahead and get started on this let's see. So we're going to take care of this real fast. This is just going to be x. So we're really focusing on the integral of 8x plus 10 over x squared minus 3x minus 4. But in order to do partial fractions, we need to fully factor everything here. So what is this going to factor into? That's right. Okay. So now that we have this, we're going to use partial fractions to split it up. All right, so let's see. Let's go ahead and get a here. So the x value for a is going to be 4, right? So what I do is I plug 4 into here, and then I divide by 4 plus 1. So I end up getting somewhat awkwardly 42 over 5. That's kind of a weird fraction. All right, and then for b, I do the same thing, only this time I'm going to plug in -1. So I plug -1 into everything except for that. And so I get -8 plus 10 is 2. And then I divide by -5. So I end up getting -2/5 for b right there. Does it matter which order you do them? Absolutely not. Yeah, as long as you get one of them to be -2/5, the other to be 42/5, it doesn't matter which one you call a, which one you call b. All right. So now that we have those, then we can split up our integral here. So the integral that we had before, which has the combined fraction, can now be split into the integral of 42 over 5 divided by x minus 4. And then we subtract, and then we have the integral of 2/5 over x plus 1. All right. And then these kind of fall into the paradigm that I described earlier. If we have the integral of a constant over x plus or minus something, that will turn into natural log. So we have x plus 42/5 ln of absolute value of x minus 4 minus 2/5 ln of absolute value of x plus 1. There we go. And technically, using log rules, you could combine this into one single logarithm, but I'm not really a stickler for stuff like that. So this is totally an acceptable answer. And this will probably be more likely to be the answer that you would see on multiple choice or something. All right. Put that on the canvas, said it was wrong. Uh-oh. Uh-oh. Oh boy. Well, you know what? You guys gotta get freebie. You're gonna get points for this. So, yeah. Yeah, there we go. All right. Yeah. Thanks for letting me know. I know I need to fix this now. Okay. Sorry about that. I don't remember people complaining about this last year. I don't know. Did I make a mistake? I don't think we made a mistake. Yeah, it doesn't look like we made a mistake. Okay, yeah, that must be the quiz. Sorry about that. All right. Anyways, so let's see here. All right, I have 2 more examples I want to go through. But before we do that, I want to give one really big warning. So normally, the most common mistake made in Calculus 2 is forgetting to put plus c on your integral. But you guys actually don't have to worry about that because it's all going to be online and it's going to have something with a box and then plus c, or it's going to be multiple choice and then you're going to have plus c on all your answers. So you don't need to worry about that. So that means that the number one error that will probably be made by you guys or someone is the following. One thing I really want to warn you about. Oh, we got an Amber alert. Okay. Well, not okay. What was it saying? Oh yeah. All right. Here's the warning. Because it's kind of fitting our phones as well. Here's the warning. So we have the integral of 1 over a function is not going to be the natural log of absolute value of that function plus c. So most of the time. So for example, let's say we have our function being x squared, right? If we followed this rule, and I'm going to put this in quotes because it's not true, then we would end up getting ln of x squared plus c. But we know what the real antiderivative to this is. It's going to be negative 1 over x. And these are not the same thing right here. So in general, if you have 1 over a function, the antiderivative will not be natural log of that function. All right, but what are we doing up here then? I mean, we said that it works up here. The exception to this is the thing I wrote earlier. If you have an integral that looks like a constant over x plus or minus a constant, then that's going to be natural log. So that's okay. But if you have anything different, if this x is squared, if there's a number times this x, if it's a sine, cosine, any other different type of function, it's not going to be 1 over that turns into natural log. So this is something that people do all the time. And I guarantee you, I will put fake answers where it's just 1 over something and it's just natural log of that thing. So I will try to trick you with that. I'm just telling you right now. I will do that, but it's not true. It's not true unless it is this right here. So I just wanted to warn you guys about that right here, because this is a very common mistake in this class. So watch out for this. All right. So now that we have that out of the way, I want to do one more example of case 1. So in this one, all we're going to do is we're going to find the partial fraction decomposition. And that's what PFD stands for, by the way. Partial fraction decomposition of the following. 1 over x plus 2, x minus 1, and then x. Now, we don't need to do the integral of this. I kind of cut out the integral to save time here. We're just going to try to find the partial fraction decomposition of this right here. Yeah, it's pretty close to PDF. Yeah. All right, so let's go ahead and try this. X plus 2, x minus 1, and x. Okay, so we need to have a letter for each distinct factor here. So we have a over x plus 2, b over x minus 1, and c over x. All right, now the difference between this one and the previous examples, obviously, is that we have 3 factors now instead of 2. But the nice thing about case 1 is that it doesn't matter how many factors you have, the cover-up method is going to work exactly the same way that it did before. So for example, let's say we have a, we want to get that. This is where we're going to have x be negative 2. So I take negative 2, which makes this denominator be 0. I cover this up, and then I plug in negative 2. So I have 1 over negative 2 minus 1, and then I have negative 2 right there. So let's see, this is negative 3 times negative 2 is 1/6. All right, let's go for x equals 1. That's b right here, so I cover up the middle part. I have 1 over 1 plus 2 times 1. That's going to be 1/3 right there. All right, and then finally, what am I going to plug in for the last one here? 0, right? This one's a little bit different because it doesn't have plus or minus something, but that just means it's effectively minus 0. So we're going to plug in 0. So I cover up this last term here, and I have 1 over 0 plus 2 times 0 minus 1. So that ends up being negative 1/2 right here. So there we go. So this means my partial fraction decomposition is 1/6 over x plus 2 plus 1/3 over x minus 1 minus 1/2 over x. And even if I did ask you guys to do the integral of this one, this would not be too bad because all 3 of these do fall into this category right here. So you can actually say it is the natural log of those guys. So that's okay. With stuff like this, it's okay. But we're going to see some examples where it may be tempting to do this for things that aren't linear functions right here. So you gotta be on the lookout. All right, I think everyone gets case 1. I think it's pretty clear how that works. Yeah, what's up? Well, you can imagine that your constant for that case is 0. So we have x plus or minus 0, for example. So you see, you could do that. For oh, because then that doesn't match. So we had a question, why can't I just put b equals 0 here to make this fall into the category? The thing that would be different is the fact that x is squared. We can only have x to the first power when we're doing this right here. It has to be exactly x. All right. Any other questions before we move on from case 1 here?
What if we had like a over the square root of x squared plus b squared?
That would be a very good one for trig sub. So if we had like something like this, yeah, that would be really good for trig sub. Remember, we cannot split the square root over the addition. But yeah, oops.
That's right. That's right. I forgot. Okay.
All right. And then yeah, we have a question in the audience. No, there cannot be. But if you do have one, like let's say we had, oh, sorry, from the comment for the audience is, what if we have a number in front of the x? What you could do is you could factor that number out of the integral, like make it like 1 over that number, and then could just combine it with the numerator. So you could kind of do that, but you need to do some legwork first. But yeah, you need to make it look like this before you could do the integral, like that. All right, let's move on to case 2 here. Case 2 is where we have repeated linear factors. Okay, so what does this mean? Well, let's take a look at an example here. So for our final example here, example 4, I want to try to do the integral of 1 over x plus 2 quantity squared times x, right here. Okay. Now we might think, okay, well, this is the same thing as 1 over x plus 2, and x, right? So why can't we just do cover up with 2 of the x plus 2? So why can't we just do something like this equals a over x plus 2 plus b over x plus 2 plus c over x? So why can't we end up doing it that way? There's a few reasons for this. One reason is that if we have some constants here that we don't even know about, what we could effectively do is, since they have the same denominator, you can combine them together, and then this could be like a new constant. So then this could be like a new constant, d, and then you could just go ahead and solve for whatever d is instead. And then effectively, we just only have 2 of these, and that's not going to work out. Another reason is that if we plug a -2 for one of these, we only cover up one of them to match on the other side, and then the denominator will be 0. Yeah, I think some people in the chat are saying that right here. Yeah, so there's a few reasons why we can't do this. You're welcome to try for yourself if you like and see how it works out, or rather doesn't work out. So what are we supposed to do then? So if we can't do it this way, how are we supposed to do it? The way we're going to do it is we're going to have one copy like we normally would, so with an x plus 2, but then we're going to have another one that's going to have x plus 2 squared down there instead. So this is how we're really going to do partial fractions for this. Now, at this point, we need to begin learning about other ways to do partial fractions, because I don't know. I take it that people kind of like the cover-up method, right? Like that wasn't too bad. You just kind of plugged in a number and then you were instantly done. So it'd be nice if we could do that all the time, but unfortunately, we sometimes need to use trickier techniques to get these coefficients here. And this will be the first example like that. But we could still use cover-up to get the highest power of each factor. So what do I mean by that? Well, I have an x plus 2 and an x plus 2 squared here. Since 2 is the highest power I see that at, I can get b with cover-up. And then since I only have a single x here, x is the highest power of x that I have, I can get that with cover up. But I can't get a by cover up. We're going to need to do something else for that. All right, so let's go ahead and figure out what b and c are, and then we'll come back to a.
Wait, where did we get x plus 2 plus x plus 2 squared?
Like, why is it written like this? It's because doing it the other way, where we have like 2 copies of x plus 2 doesn't work. So in order to do this, you need 1 copy for each power going up to whatever power it is. That's how partial fractions works in this case.
Wait, so why can we cover up the C and not the A?
We could cover up c because x is the highest power of x we have. It's the only one. But a, we can't cover this up because we do have a higher power of x plus 2 here. So whenever we have a higher power of something in the list, we can't cover up to get it.
Is that x to the third or x squared? I'm sorry.
Everything's square. There's no third power. This is a square.
Right,
This is a square.
If it was x plus 2 cubed, would you put a over x plus 2 plus b over x plus 2 squared plus c over x plus 2 cubed plus
Yes,
d over x?
That's absolutely right. So
Gotcha.
for example, so let me write that out. So this is separate from the problem. So if we have a over x plus 2, b over x plus 2 squared, and c over x plus 2 cubed. That's right. So the pattern is that you have one of these coefficients for each power going up to the highest power that you have. So if you only have something to the first power like this x, well, then you only have one of them. Kind of like how with all the linear factors, we only had one of them, so they are each just one power. But if we have something cubed, we need a representative from each one of these powers, going all the way up to and including that. All right, anyways, back to our problem here. Why don't we try to get b with cover up here? So let's see here. So what's going to make the denominator 0 for this? It's going to be -2 right here. So what I do is I take this and I cover up the thing that it shares. And since it has both of these, it's going to share both of them. I cover all the x plus 2's up. And then I have 1 over just this remaining x. And since I'm doing x is -2, I have 1 over -2. So it's going to be -1/2. And from this reasoning, you can actually kind of see why we can't use cover up for a. If I covered up the same thing as a, I would only cover up one of these x plus 2's, right? But then I would try to plug in a -2 into there, and I'd be dividing by 0. That's why cover up only works on the highest powered version of each one of these. All right, so I got -1/2 for that. All right, now let's do x equals 0 to get what c is going to be. Let's see here. So if I cover up just this x right here and I put 0 in for this, I have 1 over 0 plus 2 squared, aka 1/4. All right, now I got b and I got c, but I still need to get a. And how am I going to get a? Well, here comes the second method for doing partial fractions. The second method for partial fractions is plugging in a number. It doesn't have a nice name like cover up. It's just, oops, there we go. Yeah, so we're just going to plug in a number to do this. And what do I mean? Well, we already plugged in -2 to get b. We plugged in 0 to get c. So all we need to do is effectively just pick another number to plug in for a. Now, the thing is that since we already know what b and c are, it doesn't matter what number we pick at all. So I'm going to pick a simple number here like 1. So what I'm going to do is I'm going to plug this into my equation here. All right. Where are we plugging in the numbers? We're plugging it in for x. So I have 1 over 1 plus 2 squared times 1 is going to be 9. And then I have a over 3, b over 9, and c right here. Now, since we already know what B and C are, then we could just solve to get A. How do we get x equals -2 for B? It makes the denominator 0. So if we go back up here, what makes the denominator 0? It's -2. We put that in here, that makes this 0. So then we put it over here, we have 1 over -2, like that. Why we pick 1? Because 1's an easy number to plug in. Normally, I like to pick 0 when I can, but unfortunately, we already used 0, and you can't reuse the numbers. And the ones from cover up count. So you can't, I couldn't use 0 or -2 again. So I guess a nice easy number to plug in could be 1 right here. All right. Well, if we plug in -2 for B, wouldn't it be 0? Well, since it's squared, we cover up both of these over here. That was the problem with A, is we can't plug -2 in there because we'll have a dividing by 0 over here. But since B has x plus 2 squared, we're going to cover up both of these, and then we'll just have 1 over x. And then it's okay to plug in -2. All right, let's solve for A. Let's see, so we know B is -1/2. So this turns into -1/18. C is 1/4. Okay. And then so I'm going to add an 18th, subtract a 4th, and then I'm going to multiply by 3 right here. All right, so let's see here. So it's 3 times all of this. Let's see, the common denominator for this is 36. Okay, so I have 4 plus 2 is 6, minus 9 is 3, and then times 3 is -9. And so that ends up being -1/4. And there we go. So that's going to be our A right here. So let's recap what we did. We need to make sure we understand this. And this is where it does get a bit confusing with partial fractions. We can use the cover-up method on the highest powered version of each factor. So B has the highest power of x plus 2, right? So we could use cover-up to get that. There's only one x term, so it's by default the highest one, so we can get that. But we can't get A because there is a higher power of x plus 2 going on. All right. So then let's go ahead and use cover-up for these. So I cover up the thing that it shares, and I cover up the whole thing that it shares. So I cover up the x plus 2 squared. -2 is what makes that 0, so I put that in there. I have -1/2 right here. That's how I get B. And then for C, I cover up the x instead, and I'm plugging in 0, because that's what makes this be 0. So I have 1 over 0 plus 2 is 2. I square that to get 1/4. So I use cover up to get B and C right here. And then what I can do is I could just plug in any other number I want besides the ones I already used, and I can use that to get my remaining letter here. So I plugged in 1 for x, and 1's different from these. And I could have used like 1,000,000 if I wanted to, because it's supposed to work for all x's, but it'd be awkward to put 1,000,000 in here. But I just put 1 in. And so that gave me this right here. And then I already know what B and C are, so that gave me this. And then I just solve for A. And A is going to be -1/4 right here. What happens when we have x plus 2 squared, x plus 2 cubed? So kind of like in this example here, we could only get C and D by cover up, and we'd have to get B and A by doing this. And that would involve solving a system of equations, which gets a little bit messy. We're going to talk more about that next time. All right, well, anyways, we got all 3 of these, so why don't we go ahead and put this back in our integral. Thankfully, the integral part won't be bad once we do the partial fractions. So I have -1/4, and I'm dividing by the A here. Remember, this is my original partial fraction here. So we have x plus 2. All right, and then our B was -1/2. And that was x plus 2 squared. And then finally for C, we have 1/4, and that was just x. Okay, Now for 2 out of the 3 of these will be exactly the same as the integrals we've done earlier. So for this first one, I have a number over x plus or minus a number. This will be -1/4 natural log of absolute value of x plus 2. This one I'll get to in a moment, so I'll just kind of leave it like this. And then this one is going to be 1/4 natural log of absolute value of x. All right. So then now we need to do this integral right here. So we have 1 over x plus 2 quantity squared. So whenever you have x plus or minus a number raised to a power and you want to integrate it, you could treat the whole thing as if it were one variable. So if you have x plus or minus a number, and there can't be anything in front of the x, but if you have just an x, and then we have plus or minus a number right here, then let's see here. Then what we could do is the integral of x plus or minus a to a power is x plus or minus a to the n plus 1 over n plus 1. So we can effectively treat this like it's one variable. So we don't really need to do a u substitution for this. This is going to be like 1 over something to the -2. So I could just use the power rule on that directly. So it doesn't need to just be x to a power. It could also be x plus or minus a number right here. So that means that my last integral, let's see, this is to the -2nd power, right? So I raise that by 1. And now I have the -1st power, and I divide by the new power, which is -1, which just flips my sign. Now I have this to the -1st power. And there we go. So we've gotten rid of all of the integrals right there. And now we have our antiderivative right there. All right. Yeah, you might want to mute yourself here. There we go. Okay. All right. Looks like we're out of time here. Don't worry, we're going to get more practice with this next time. So we're going to keep doing partial fractions next time. So if this seemed a little bit strange at first, we're going to keep practicing it. We're going to get better at it, and it'll get easier as time goes on. All right. So yeah, I guess I'll see you guys on Monday where we'll learn about the other 2 cases for partial fractions.
Thank you.
Yeah, see you guys later.
Thank you.
Thank you.
No problem, guys.
Thank you.
Let me change.